We'll start by looking at example 23, in which we are asked to find the cube roots of the complex number 1 plus I. And in this case, the question wants me to give it in polar form. So if you recall in the last video, if we want the answer in polar form, it is good for us to start in polar form. So therefore, in step 1, I am going to express the complex number in polar form, which means that first I must find the magnitude of 1 plus I, which is root 2, and I need to find the argument of 1 plus I, which I know is pi over 4. Therefore, in polar form, 1 plus I can be written as root 2 times of cosine pi over 4 plus I sine pi over 4. The next thing we are going to do is to generate the extra n minus 1 versions of W by adding 2k pi to the argument. So this tells me that I can also write W as cosine pi over 4 plus 2k pi. In the end, after I consider the principal value, it still falls back to the same complex number. Okay, so after generating all these, I have to specify what are the values of k. So let me allow k to be 0, 1, 2, and where should I stop? In total, I should have 3 different roots, so it is good enough to stop at k equals to 2. Because as we can see, this gives me a total of 3 different starting values of W. Each one of these values will later on give rise to one root of W. Now we move on to the next step, in which I'm going to use De Moivre's theorem to find the cube root, and therefore it means that I'm going to raise it to the power of 1/3. So if you recall, the modulus of Z would be the modulus of W to the power of 1/3. So this is 2 to the power of half to the power of 1/3, which is 2 to the power of 1 over 6. Whereas the argument of Z would simply be the argument of W over 3. So this will give me pi over 4 plus 2k pi, whole thing multiplied by 1/3. And upon simplifying this, I will get pi over 12 plus 2k pi over 3, which is how I arrive at the next step over here. And bearing in mind the values of k are 0, 1, and 2, I have therefore arrived at a total of 3 different roots. And let's take a look at how these roots are going to be distributed. The first root is going to be when k equals to 0, so the argument of this root is going to be pi over 12. Okay, so let's say this is the first root, and this angle is going to be pi over 12. What is the next root going to be then? It's going to be at k equals to 1. That means it's going to be pi over 12 plus 2 pi over 3 when k equals to 1. Okay, so that gives me 2 pi over 3 is actually 120 degrees. So I know it's going to go roughly 120 degrees, and it's going to be somewhere here, but the modulus is still the same. Okay, so this is going to be probably be my second root. And my third root, I am going to add another k equals to 2. So in this case, I'm going to add 4 pi over 3. So from here, if I were to add 4 pi over 3, this is if I add 2 pi over 3, and if I were to add another 2 pi over 3, I would likely end up somewhere here. So this is my third root, and as you can see, it forms the triangle relationship where they are all equally distributed about the origin because of the way in which the argument varies by steps of 2 pi over 3 each time. Okay, and in this way I have obtained the 3 different roots. Now there is one last point to take note, which is that if you recall, the argument of each root must fall within the principal range. Okay, so the argument of Z must fall within negative pi and pi. So let's do a quick check. Definitely this fulfills the criteria, and this also fulfills the criteria, but this one, 17 pi over 12, we find it exceeds this principal range. Okay, it is actually greater than pi. So what can I do now? Because of this, you recall we can add 2 pi and subtract 2 pi without changing anything. So instead, if I were to subtract 2 pi, I would go back one circle and end up at the same point. Okay, and that will actually give me negative 7 pi over 12. And therefore, instead of expressing it in this form, which is not acceptable because the argument falls outside the principal range, I will just use this argument instead, which is an equivalent expression. The complex number is still the same one. Notice that instead of using 0, 1 and 2 for the values of k, you recall that I also mentioned that we can use 0, 1 and negative 1. Okay, because then my values of k will be as such. So let's see what will happen if I do this case. Doing the substitution, you'll find that I directly get the 3 correct values, and very nicely, the 3 arguments do not fall outside the principal range. And the thing that we notice is that the roots obtained are still the same, even if I use these values of k instead. Okay, so now there's an extra question. Let's think about this. Can I use k equals to 2, 4 and 6? Am I going to still get the 3 roots? And you would find that this is not acceptable, because then I would have skipped certain values of k. So in this case, if you were to use 2, 4 and 6, you will find that the change in argument is no longer 2 pi over 3. Okay, which means that your roots will not be evenly spaced about the origin. So what does that tell me about the values of k that I can use? In fact, what I'm trying to tell you now is that the values of k must be consecutive. Okay, in this case, we need 3 consecutive values of k. Okay, but in general, if we have the nth root, we will need the n consecutive values of k.